So, welcome back to the advanced manufacturing and process modeling course. So, we were discussing about additive manufacturing. So, we have already discussed about the additive manufacturing variants, and also the two prime variants we discussed in detail, that is laser powder bed fusion and directed energy deposition, which are mostly applicable for developing metallic structures. So, now we will start with the interdependence of several process variables involved in case of additive manufacturing, and also how to model them, how to develop process models to understand grab insight into the process physics of additive manufacturing and how to optimize the process conditions as well. So, to serve both the purposes. So, let us go to the key notes on processes. So, you can see the process parameters. So, the process parameters are laser power, scanning speed, layer thickness, hatch space, laser spot size, etc. And then feedstock consideration. So, powder bed and powder stream generation, and then laser interaction, that is laser absorption by powder bed, powder stream, melt pool considering multiple reflections and beam shadowing, and then transport phenomena. So, transport phenomena is thermokinetic and thermofluidic evolution of single or multi-layer, single or multi-track during LPBF, laser powder bed fusion, and laser DED, directed energy deposition. So, the objective is defect mitigation and process optimization. So, then how we can accomplish the goals? So, we can do that by CFD modeling of additive manufacturing. So, the primary objectives are predicting melt pool evolution at the mesoscale, analyzing the consolidated track geometry and process parameters, appraise defects such as predict and also if we can successfully predict the formation of these defects, we can also tune the process parameters to nullify or to control these defects such as porosity, denudation, track instability, melt spatters and other physical events, and provide thermal history for thermometallurgical models and also thermomechanical models to estimate part scale characteristics. So, these are the prime essence of developing computational fluid dynamics based numerical models of solidification transport phenomena in case of additive manufacturing. Okay. So, the assumptions for numerical framework, number one is melt pool behavior. So, which is treated as incompressible. So, what is incompressible? We know that density remains constant. Okay. Fluid flow is assumed to be in a laminar regime. So, that means the as we know that means the Reynolds number is essentially less than 2100, and as you know that Reynolds number is nothing but rho v d by mu, where rho is the density, v is the velocity, d is the characteristic length or the distance, and mu is the dynamic viscosity. So, and then number 2 is the material properties. That is regarded, the material is regarded as isotropic, and thermophysical properties of powder and substrate depends on the temperature, and then dynamic viscosity is temperature independent in the molten metal. Okay. So, these are the considerations in material aspect, and number 3 is laser absorption. So, absorption by the vapor plume if present is neglected. So, and then conservation equation. So, transport phenomena in laser additive manufacturing are calculated by solving the conservation equation of mass, momentum and energy. So, likewise we have discussed in case of casting and also discussed in case of welding. So, now we are going ahead with additive manufacturing to develop the process model by solving the basic conservation equation of mass, momentum and energy. We also need to solve species in relevant occasions. So, then mass conservation is basically the equation you are familiar already with it. So, del rho del t plus grad rho u is equal to 0. So, where rho is the density of the material, and u is the basically the velocity, molten metal velocity. Okay. And then number 2 is momentum conservation. So, which is rho del u del t plus rho u u grad u dot grad into u is equal to minus delta delta p plus I mean mu grad square u plus grad u into I minus rho into 1 minus beta T minus T m G plus F bar. Okay. So, I mean so here I mean so then I mean so here you can see that the T m here is the melting temperature and T is the absolute temperature, and then I mean so P is basically the pressure. Okay. So, delta minus grad P. So, that is basically the pressure, and then I mean so energy conservation. So, energy conservation equation is rho Cp del T plus so capital T is for temperature, small t is for time, and Cp is the specific heat of the material, okay, plus rho Cp u I mean grad T is equal to grad K grad T plus Sh, where Sh is I mean basically is a source term. So, then I mean that we will be discussing later, and then where Darcy damping force F is equal to minus C 1 into 1 minus FL by FL cube plus B into U. So, and then liquid fraction calculation FL, so which is equal to 0 when T less than equal to Ts. So, Ts is the solidus temperature, and I mean FL is equal to T minus Ts by TL minus Ts when T greater than solidus temperature, less than TL, that is liquid, less than equal to TL, that is I mean liquidus temperature, and FL is equal to 1 when T is greater than liquidus temperature TL. Okay. So, I mean so then here comes the laser heat source equation. So, in laser additive manufacturing, the spatial intensity distribution of the laser beam typically follows the I mean TM00 Gaussian mode. I mean so the heat source term is represented as I mean SHR is equal to G eta q by pi r square r beam square exponential minus G r square by r beam square. So, where G is the heat source distribution factor, eta is the laser efficiency, and r beam is the laser beam radius. Okay. So, I mean so the applications, so laser powder bed fusion, the equation is integrated using the ray tracing approach to calculate heat distribution. LDED, laser directed energy deposition, it incorporates beam attenuation coupled with the DPM, discrete phase model or discrete particle model, to determine the heat source term, and considers additional heat from molten particles. Okay. So, I mean so then moving ahead, we will talk about the cooling. So, the heat radiation effects during laser additive manufacturing are modeled using a nominal gray body radiative cooling term included in the energy equation. So, like I mean so where we have seen in the previous equation, okay, in the energy equation. Okay. So, then so this is basically the I mean heat source terms in the energy equation SH, and with that these cooling terms are also I mean present. So, then I mean so then I mean so S radiative is basically is equal to epsilon I mean sigma E T4 minus T ambient to the power 4, where epsilon is the emissivity of the material, and sigma E is the Stefan Boltzmann constant, and T is the temperature of the surface, and T ambient is the ambient temperature. And then so convective cooling. So, additive ambient cooling effects are modeled using the standard standard convective cooling term. So, S convective is equal to H T minus T ambient. So, H is the heat transfer coefficient where and which varies between I mean 10 to 100 watt per meter square Kelvin. So, I mean so here please correct. So, it will be 10 to 100 watt per meter square Kelvin, and T is the temperature of the surface, and T ambient is the ambient temperature. Okay. So, I mean and then heat removal through vaporization. So, so a significant amount of heat is removed from the melt pool by escaping vapor particles during vaporization. So, the heat removed I mean that is QE vapor is calculated as I mean Q evaporation is equal to mv into lv, where mv is the vaporized mass flow rate and lv is the latent heat of vaporization. So, now what is the vaporized mass flow rate mv? So, it is basically described by the Hertz-Langmuir relationship, and what is that? So, Hertz-Langmuir relationship speaks that mv is equal to root over small m by 2 pi kb Ts into P saturation which Ts into 1 minus beta r, where small m is the mass of a vapor particle and Kb is the Boltzmann constant, Ts is the surface temperature, P saturation Ts is the saturation vapor pressure at surface temperature Ts, and beta r is recombination coefficient. Okay. So, so these are the detail of the mass transfer mass flow rate calculation, and then the saturated vapor pressure P saturation at temperature Ts, that is surface temperature, which is described by Clausius-Clapeyron relationship. So, here P saturation at Ts is equal to P atmospheric pressure into exponential delta Hv by Kb Tv into 1 minus Tv by Ts, okay, where delta Hv is the enthalpy of vaporization and Tv is the vaporization temperature and Ts is the surface temperature as spoken earlier, and Kb is the Boltzmann constant, Patm is the atmospheric pressure, and then retro diffusion coefficient beta r. So, so it represents the fraction of vaporized material that recondenses. So, beta r is equal to 1, all vaporized material recondenses, that means mass flow rate of vapor, that means vapor phase mv is equal to 0 and beta r is equal to 0 means no recondensation occurs, that means strong vaporization happens in that case. So, then if we go to the recoil pressure, so the vaporization induced recoil pressure can be expressed in terms of the saturated vapor pressure. So, it is worthwhile to note that the recoil pressure acts on the liquid vapor interface and is included as a source term in the momentum equation. Okay. So, you can see like we have discussed earlier about the momentum equation. So, then here you can see the source term that is shown over here, that is the F is the source term where it is included. Okay. And also so the recoil pressure is can be calculated from the vaporization in so that P recoil pressure recoil is equal to 1 plus beta r by 2 into P saturation at surface temperature Ts. Okay. So, now moving ahead, the role of surface tension. So, surface tension is responsible for the normal stress on the melt pool surface dependent on its curvature. So, so gradient of surface tension. So, it acts as a tangential stress or Marangoni stress, which is very important to determine the shape of the melt pool and also the microstructure formation from there on. Okay. So, so it is included as a source term again in the momentum equation. How? That is so what is the surface tension source term, that is S sigma is equal to sigma. So, so please correct it, it should be S sigma is equal to sigma Ks n plus d sigma dt into grad T minus grad T dot n multiplied by n, where sigma is the surface tension, Ks is the surface curvature, n is the surface normal and d sigma dt is the temperature dependent surface tension coefficient. Okay. So, so equations for surface tension mechanism. So, surface tension equation sigma is equal to sigma m minus sigma y or sigma r whatever into T minus T m minus R g T this gamma s ln 1 plus k l k l a I e to the power minus delta H 0 by R g into T. So, temperature coefficient of surface tension is d sigma dt is equal to minus sigma r minus capital R j T gamma s ln 1 plus k l l minus k a I by 1 plus k a I into gamma s delta H 0 by 1 by delta H 0 by T, which can also be so simplified so into the expression that is depicted over here, that is d sigma dt is equal to minus sigma r minus r g t gamma s k a I delta H 0 by 1 plus k a I into t, okay, where equilibrium constant capital K is equal to k 1 exponential minus delta H 0 by r g t, where gamma s is the surface excess saturation, A I is the activity of the impurities, delta H 0 is the standard heat of adsorption, R g is the gas constant, and K 1 is the entropy of segregation constant. And so where sigma m is the surface tension of pure metal and sigma r is the temperature dependent surface tension coefficient. Okay. So, I mean, so this is a typical example that has been done in our research group. So, you can see this is a typical single track, I mean this build of laser in case of laser powder bed fusion of titanium alloys. So, you can see the with the progress of laser movement how it cures the powder bed and creates a, I mean single layer build. Okay. So, single layer build. So, you may see look into the publication to grab deeper insights, and this is a typical boundary condition. So, I mean in different directions of the powder bed that is considered for the LPBF simulation, where laser power of 310 watt and scanning speed of 100 semi per second were considered. Okay. So, I mean so these are some of the results obtained from the simulation studies. You can see the longitudinal profile, that is the simulated result, and also you can see the corresponding experimental, I mean validation, which depicts the accuracy of the numerical findings simulation results. So, apart from longitudinal profile, you can see the cross section, or more specifically the bead cross section. So, there also, I mean you can very well understand the accuracy of the developed process model, or rather it is the role of the process model which can effectively capture the, I mean this bead dimension and also the, I mean build geometry, and thereby it can also provide a insight about the, I mean quality characteristic in terms of I mean macroscopic features or macroscopic dimensions of the deposited build, and also thereby it helps to optimize the, I mean process variables in case of LPBF, like I discussed with you earlier, like laser power, scan speed, I mean spot radius, and also I mean like I mean powder particle morphology, and yeah. So, these are the, I mean important variables, and also the layer height, etc. So, I mean so now we have already discussed the essence of process model to understand the, I mean thermofluidic I mean conditions, and also the solidification micromechanisms, mass transfer heat and mass transfer conditions in case of additive manufacturing. So, now we will learn how the outcome of the this CFD model can be utilized as input to the I mean this mesoscopic phase field model to simulate the microstructure that evolves in case of multi-layer additive manufacturing processes. So, so metal additive manufacturing has driven huge attention in recent decade in the field of biomedical, automotive and aerospace industries. So, because of its efficiency of making complex parts. So, we have discussed about this I mean the introduction of AM already. So, I mean like so in case so these are the different AM techniques like LPBF, EPBF and also DED and WAM, wire arc additive manufacturing. So, where high energy heat source such as laser or electron beam is used, the process microstructure property. So, this is a key phrase. So, then so there is a dependence of the evolved microstructure on the process, and then microstructure determines the mechanical property. So, there is a threefold interaction you can see over here. So, this relation is very important for fabricating components from metals and alloys. The physics behind the formation of complex microstructure in additive manufacturing process can be explored using phase field method. So, the knowledge of microstructure evolution during multi-layer formation, formation of secondary phases and defects, coupling between successive layers, grain orientation in additive manufacturing process are very useful to develop process microstructure property relationship in case of additive manufacturing process. Okay. So, so then the introduction. So, the basic steps involved in additive manufacturing process is to move a heat source, that is laser or electron beam, on a powder bed on some selected tracks, followed by CAD modeling. So, and then melting and solidification during layer by layer growth process. The scanning parameters such as laser power, velocity and the geometry of the melt pour are some key controlling the microstructure of the additively manufactured material. So, so then so now we will go into the microstructure formation mechanism. So, prediction of microstructure is very important in the study of additive manufacturing process, because the thermomechanical properties of the fabricated components and are highly dependent on the microstructure. So, that is why we were discussing about the processing microstructure property correlation, that have a immense importance in understanding and optimizing additive manufacturing processes, and also to identify the desired quality characteristics. So, which is microstructure and the property of the developed builds or parts. In a two dimensional phase field simulation, the microstructure evolution in a cross sectional area of the powder bed in a single track perpendicular to the direction of movement of heat source is generally considered, and during laser scan temperature rises sequentially in the perpendicular direction, that means from the base to the top of the melt layer or the powder bed. So, in the direction to the movement of heating source, that is from top to bottom, which results in melting of the powder in the present layer as well as a certain thickness of the previous layer. So, that is what I was discussing about remelting in the beginning in the previous class. So, we will learn how to simulate the microstructure formation in case of remelting, in case of formation of the subsequent layers. So, with removal of heat, solidification begins from the bottom of the molten region of the previous layer, and the microstructure formed in a layer is dependent on the microstructure formed in the previous layer. So, often we see epitaxial growth in case of laser additive manufacturing. So, because of the favorable crystallographic growth orientation, and and also because of the presence of the G by R ratio at that particular layer. So, a discontinuity generally appears in the microstructure in the region where the growth in the previous remelted layer starts. Okay. And the change in this grain orientation at the interface is as a result of the thermal and solute conditions at the remelted interface, which influences the nucleation and growth of new dendritic structures. Often more than nucleation, it is the growth, and the growth in the epitaxial manner, that is what has been observed in case of multi-layer laser additive manufacturing. Okay. So, this is a typical schematic diagram for multi-track and multi-layer AM. So, this is, you can see that this is a multiple tracks are made, and then over the multiple tracks then multiple layers are getting deposited. So, that is why we are calling it as multi-track multi-layer AM. And the schematic diagram or thermal phenomena in AM. So, you can see it is a fairly complex, that thermal conditions prevails in case of laser additive manufacturing. Here this schematic speaks about laser powder bed fusion that we have discussed in detail earlier. So, so this is basically the powder bed which is deposited, and then the laser beam, the energy source moves over it at a predefined scan path, and then it melts and cures the material, and that facilitates microstructure formation in the solidified layer. So, how it forms, that we will try to discuss. So, the grain morphology, columnar grains are dominating microstructure in additive manufacturing process, whereas equiax grains are desired microstructure in ordinary casting and welding processes, that we have discussed already. So, why? Because in case of additive manufacturing, it is the DS directional solidification that takes place, because it happens in layer by layer fashion, that we have already discussed already, because there is a tendency of growth of grains opposite towards the maximum thermal gradient. So, that is why, so that because temperature is higher from bottom to top. So, the equiax grain structure, so the high energy associated with selective laser melting or electron beam melting results in a steep temperature gradient from the solid liquid interface to the melt, and this high temperature gradient favors formation of columnar grains, and that is the reason why in case of additive manufacturing we mostly see columnar grains, rather than in case of conventional casting and also in case of most of the welding processes, where we see equiax grain structure, which results due to the nucleation of randomly oriented grains growing in all direction. Okay. So, so these are the typical etched dendritic microstructure of single track, single laser track in case of laser powder bed fusion, and then this is the corresponding EBSD map of single laser track. So, where you can very well see the epitaxial growth. So, this is epitaxial growth of columnar dendrites or cellular dendrites. Okay. So, and then so the effect of temperature gradient and solidification velocity. So, with removal of the heat source, the temperature of the melt pool varies spatially as well as temporally. The powder bed fusion process is associated with very high cooling rate, which is typically of the order of 10 to the power 6 Kelvin per second. So, this high cooling rate results in very high velocity of the solid liquid interface, and the terminology the morphology of the solidified material processed by additive manufacturing is dependent on the ratio of the local temperature gradient G and the local solidification front growth velocity R. So, that is G by R, that we have discussed earlier. So, that means the morphology depends on G by R, whereas the size depends on G cross R. Okay. So, then these are the two prime conditions which determine. So, G cross R determines the size of the evolving crystals or grain, and G by R determines the shape of the evolving grains. Okay. So, so for higher value of the G by R ratio, planar solidification front stabilizes, and however, with increase of solidification velocity, the planar solidification front becomes unstable and result in columnar structure. The columnar structure may be cellular or cellular dendritic. The primary phase morphology significantly influences the morphology of precipitate phases. Okay. So, so this is basically the typical dependence of shape and size of the solidification microstructure in case of additive manufacturing. So, you can see the dependence of grain morphology on the values of temperature gradient G and the solidification velocity R. Okay. So, you can see that at a high G bar R ratio, it is the microstructure is planar, and with the decreasing G by R ratio, it transitions into cellular, from there to cellular dendritic, from there to columnar dendritic, and then when even at even lesser G by R ratio, it moves to the equiax dendritic structure. So, that is what I was discussing earlier. G by R determines grain morphology, and G cross R controls grain size of the solidified microstructure. Okay. So, and so this is a typical melt pool depth during formation of two consecutive layers. So, you can see over here. So, this is what I was discussing earlier. So, you see, although the deposited layer thickness is this much, say the deposited layer thickness is say H. However, when the heat source, the laser source impinges over the typical layer, so then it penetrates even deeper. That means it differs more than the H. So, in case of first layer, it impacts some amount of melting to the substrate plate, and with the subsequent layer deposition, it impacts the previous layer already deposited, and it causes remelting of the solidified microstructure of the previous layer. And so, that is also facilitates fusion, and also because of remelting, it also promotes epitaxial growth of microstructural features. Okay. So, from the remelted zone, the dendrites starts growing in a epitaxial manner. Okay. And here this is a typical temperature variation at point P. So, you can see this is the point P, and for it, so you see during different layer formation. So, Tm represents the melting temperature. So, as you can see that for nth layer, so this is a n layer. When nth layer deposition, because it is in liquid state, you see the temperature goes higher than the Tm substantially, and then goes down when it gets solidification, when it undergoes solidification, and when layer n plus 1 gets deposited. So, then as I told you earlier that the some depth of the previous deposited layer, the solidified microstructure undergoes remelting. So, you can still see that at point P the temperature goes beyond the melting temperature even when the second layer is getting deposited, and then it cools off during solidification. However, when the subsequent layers getting deposited at the top of these two layers, like n plus 2 layer or n plus 3 layer, so there is the temperature, of course temperature grows bigger from the room temperature, but it does not cross the melting temperature. So, that means no further remelting happens in the layer which is immediately which is, so that means it can know that we have to adjust the laser intensity in such a way that the remelting only happens in the layer immediately beneath the layer which is getting deposited to facilitate improved metallurgical bonding between the two adjacent layers. However, that should not penetrate deeper, the layer which is even below. Okay. So, this is the basic concept, and then coming back to the microstructure modeling. So, the field variable in case of phase field modeling, the field variable phi which is a function of both space and time distinguishes the phases present in the domain, computational domain. So, where phi is equal to 1 represents solid phase, phi is equal to 0 represents liquid phase, and a transformation from 0 to 1 happens over a diffused interface of thickness eta. So, then so the phase field model is a diffused interface model. It is unlike other models where sharp interface is described between the solid and liquid phases. In case of phase field model, it is the diffused interface that is what considered between the solid and liquid phases. So, you see that here if we plot the phase field parameter phi with the spatial with respect to the space, that is x. So, you see that at solid it is 1, and then at liquid it is 0, and it transitions between 1 to 0 when it is going through the interface of the solid liquid interface. Okay. So, it transitions from 1 to 0, and what is the velocity of there? It is v is equal to phi dot by grad phi. Okay. So, so then moving ahead with the governing equations. So, that we will be covering in the next class. So, for this class we are stopping here, and in the next class we will be discussing about how phase field model can be developed to predict the microstructure of the additive manufacture build, and especially in case of LPBF we will also discuss about with some case study that has been performed within the scope of our group's research, that how the solidification microstructure develops. So, till then, thank you and see you next time.